Hi guys, I just wanted to give you some review videos for the lessons that we've talked about so far in this unit on motion and forces. So I have Think Central pulled up right here. You'll see lessons 1 through 5. I'm just going to give you kind of the main points from each of those lessons so that you can study for your test, which will take place tomorrow. So without further ado, let's go ahead and start on lesson 1, which is on motion and speed. Okay, so lesson 1, if you were at all confused about motion, basically motion is just any change in an object's position. Now, in order for an object to be moving, we need to understand its reference points around it. So motion is just the change in position of an object relative to its reference point. So even though you're sitting next to someone on a plane, it does not appear to you that they are moving because they're not changing from your reference point. But to someone on the ground, someone in an airplane is definitely moving. So reference point is definitely important in determining motion. So we got motion, but to describe motion, we use different kind of units. So we measure motion in terms of distance, and to help us understand distance and how things are moving, we also measure time of motion. Okay, that brings us to our second definition, which is speed. Okay, speed is just simply the change in position of an object in given amount of time. Okay, so we can start to look at a formula for this. We haven't really talked about instantaneous speed or speed at any given moment. We've only talked about average speed. Okay. The average speed, there's a formula associated with it. I'm going to run you through that right now. The average speed is calculated as the final distance minus the initial distance over the amount of time it took to cover that distance. Okay? So be able to plug values into that equation to calculate average speed. If you remember where we went next in this discussion, we next talked about velocity, which is basically speed with a direction. Okay, velocity was the first of our vector quantities. Vector quantities depended on direction. Okay, so velocity is a vector because it depends on direction. Okay, the formula for velocity is the same for the formula for speed. Okay, so we're still going to do equals df minus di over the amount of time, but remember velocity always has to have a direction associated with it. So it could be 6 meters per second south or 6 meters per second up, whereas speed is just 6 meters per second. Okay, just focus on the direction there. Okay. I think that pretty much does it for lesson 1. Let's move on to lesson 2. Okay, so lesson 2 talked about an object's acceleration. Okay, so simply put, acceleration is the change in velocity of an object over time. Okay, the formula associated with acceleration, A equals your final velocity minus your initial velocity over the amount of time. So it looks very different, or it looks very similar to our formulas for average speed and velocity. Remember, this is average acceleration. Now there are a couple instances where acceleration kind of defies what we normally think about it. So for example, you're probably used to acceleration being used to explain something that is speeding up. But acceleration can be in the negative direction because it is a vector quantity. Okay, so when you're decelerating, in other words, when you're slowing down, you still have acceleration. It's just in the negative direction. Okay, so I'm just going to put a bullet point in here that says can be negative based on direction. And if you remember the other special case of acceleration, acceleration also changes when going around curves. Even if you're going at a constant speed, if you go around the curve, because you're changing direction, you're changing acceleration. Okay? So affected by curves. Cool. Let's see here. Was there anything else we talked about with acceleration? Acceleration around curves or around a circle is called centripetal acceleration. So whenever you see the word centripetal, think circle, because that's what it's describing. Okay, feels good. Let's go on to forces. This is lesson 3 on Think Central. So there's forces. Now forces are basically best defined as a push or pull on an object. Okay? So whenever I draw pictures to demonstrate forces, I like to do arrows. So let's say I've got a box and I am pushing this box with my little stick figure in this direction. Okay, so that's an example of a force. So my diagram is kind of might be confusing because it shows the force dragging the box along, but just imagine that I'm pushing the box in that direction, so the force is going in that direction. Here's my little F for force. Now, any object that you have in front of you or in the same room as you right now is being affected by a force. Okay, so this box in my example, if this box is on the floor next to me, it's experiencing a downward force due to gravity. So I'm just going to put F grav for the gravitational force. Now, because the box isn't crashing through the floor and going towards the center of the earth, some force must be also pushing up on the box to keep it in place. We usually call this force the normal force, and it's kind of opposite to the gravitational force. We also see that when we try to move objects across a table or across a rough surface, we experience a frictional force. Okay, friction is a force that increases as you go across like carpet, because carpet's kind of coarse and pushes back on you. But if you're going against a really smooth surface, the force of friction is very, very low. So those would be the forces acting on this box as I try to push it. Gravity, the normal force, and friction, as well as the force that I'm exerting on it. Okay? Whenever we have all the forces an object is experiencing, we can calculate the net force. Okay, the net force is just the sum of all forces on an object. Now, be aware that because these forces have directions, force is also a vector quantity. So to calculate the force, the net force on this object, we would need to know the numbers for, the magnitude of the force. So let's say I'm pushing this box with a magnitude of 20 newtons, and let's say that the box has a gravitational force of like 100 newtons, and that would make the normal force also 100 newtons. And now let's say that the frictional force, or the force exerted by the surface against my push, let's say that force is only 5 newtons. Okay, so if you add up all these forces, well, 100 going up plus 100 going down, those will cancel each other out. We got 20 going in this direction. We got 5 going in this direction. Okay, well, since 5 is going opposite from 20, we can just subtract the 2. So the net force is 15 newtons going in this direction. So just remember to add up the forces, and remember where a direction's going so you can subtract when needed. Okay? Hope that makes sense. Let's see, where were we going next? Forces. Okay, that sounds good. So, when we talk about forces, we launched into a discussion about Newton's laws. Okay? So let's talk about those real fast. Newton had 3 laws. First law, so Newton's first law says this. An object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by an unbalanced force. Okay? So the reason we know this concept is true is because when we I think the example in the practice test they gave you was if you have like a playing card that's resting on a glass and you have like a coin sitting on top of that playing card. Imagine flicking this playing card out from underneath the coin. Now some people might suppose that the coin will flick with the card, but because of Newton's first law, that coin, which is initially at rest, will want to stay at rest. So the card will literally fly out from underneath the coin, and the coin will drop into the cup. Try it out at home, and you'll see Newton's first law in action. Okay? That's Newton's first law. We also talked along the lines of Newton's first law. We talked about a property called inertia. If you remember what inertia is, it is the tendency of an object to resist changes in its motion. Okay? So because the coin obeys Newton's first law, it experiences inertia when that playing card is flicked out from under it. Okay, let's go on to Newton's second law. Okay, Newton's second law. Newton basically said that an object's acceleration is influenced by the force on it along with its mass. Okay? And he used an equation to describe this. The equation looks like this. Force is equal to mass times acceleration. Okay. So, the practical example that we gave in class, imagine you have a baseball bat, horrible baseball bat, and let's say you have a baseball. Now if you're swinging the bat at this baseball, as soon as the two make contact with each other, they are exerting forces on each other. The bat is exerting force on the ball is exerting a force on the bat. Now, Newton's third law is going to explain how these objects interact with each other. But you'll notice that the mass of the bat is bigger than the mass of the ball. Because the mass of the ball is so much smaller than that of the bat, the acceleration due to that force between the two objects will accelerate the ball much more than it will the bat. Okay? So basically, smaller objects, or less massive ones, accelerate more than more massive objects. Kind of makes sense. So when that bat hits the ball is going to go zooming off, and the batter may feel the bat recoil a little bit, but it's not going to go flying out of their hands like a ball was flying, because it's not experiencing as much acceleration. Okay, let's talk about Newton's third law. Newton's third law says every action has an equal and opposite reaction. So, using our baseball example, up here, when the baseball collides with the bat, there's a force being exerted on the bat. Notice the little arrow I'm drawing. And there's a force being exerted on the ball by the bat. Okay? Now, believe it or not, these two forces are equal and opposite to each other. Now, the reason, you might not think that since the ball goes flying off and the bat stays generally where it is, but the reason the ball flies off is because of Newton's second law. But the forces between the two objects are the same. Think about a pool ball scenario where you're playing pool. If you're striking the cue ball at another ball on the pool table, the collision between the two balls involves forces that are equal and opposite, even though one ball goes flying out and the other one kind of stays where it is. Okay, that's Newton's third law. Newton's laws, just be able to apply them to situations, be able to identify which law is being referenced in a particular situation, and you'll do great. Next thing we talked about on Think Central was gravity and motion. Okay, so gravity, as we've already talked about, is just the force exerted between two objects. Now notice I didn't talk about the Earth, because really any two objects on Earth have a gravitational force between them. The shoe in front of me right now is exerting a force on this tablet I'm holding, but we don't see the two go towards each other. We don't see the two objects pulling on each other because there's other forces at work that are preventing that from happening. You've got the force of the Earth down below me. Let me draw a picture, just in case. Kind of what I'm saying is kind of losing you. So that's my shoe. Once again, horrible shoe, but it'll make do. And let's say here is my computer. Okay? My keyboard. Okay, so right now, there is a force that's pulling my computer towards my shoe, and there's a force that's pulling my shoe towards the computer. But at the same time, we've got a much larger force being exerted by gravity on both of these objects, which is basically going to overcome any chance these objects have of moving towards each other. We've also got friction acting on each object as it tries to move. Okay. We've also got the normal force being exerted on these. So you can see there's multiple forces that are coming into play, which basically overpower the gravitational force between these two objects. Okay? But the main point is, realize there is a gravitational force between them. Now, if these two objects were the only things in the universe, and there were no other forces to compete with, sure, these objects would eventually find each other. But they don't because of the Earth and all the other forces acting on them. Okay? Now, just like any force, Newton said that any force could be described by the equation force equals mass times acceleration. Well, it turns out that the Earth has a specific acceleration value for every object that's being pulled by gravity. Its acceleration is always negative 9.8 meters per second squared. Don't worry too much about the units. Okay, when you get to physics class in high school, your teacher can go a lot more into why the units are the way they are. Just worry about knowing the number and the units. Just don't, once again, don't worry about why. Now, if every object experiences the same acceleration due to gravity, then theoretically, a bowling ball and a feather should experience the same acceleration when dropped off a tall building, which is true. So why don't we see the objects falling at the same rate? Well, the reason is because the bowling ball is much more massive, so it's a greater force is being exerted on it. Another reason why the bowling ball falls faster is because the feather experiences a lot of air resistance as it falls.
So, but if we were in a vacuum, like in outer space, and we toss these two objects across, a void of empty space, they would go at exactly the same rate because there would be no air resistance to keep the feather from moving just as fast as a bowling ball. So that's how gravity kind of influences objects on the Earth. They all have the same acceleration, just different forces and masses. So because acceleration is constant on the Earth, we like to replace A with G, just to remind us that we're talking about gravity. So here's kind of your next equation. Force equals m times g, which is basically just the mass of an object times negative 9.8 meters per second squared. Okay. So the other thing I want to talk about with gravity is a case of free fall. Any object in free fall is only being acted on by gravity. So free fall means the only force in effect is gravity. Okay, so a skydiver jumping out of a plane is experiencing free fall. When I'm dropping my pen from any height, it's experiencing free fall. Now, don't get too technical with it because yes, there is air resistance acting on every object as it flies through the air. But for all intents and purposes, just think about free fall. Okay? The other example of free fall we gave was kind of counterintuitive, but any satellite that's orbiting the Earth is in free fall. Now, if gravity is always acting on a satellite at every point above the Earth, a lot of people might think that the satellite should, in theory, be crashing towards the Earth or getting closer and closer. But the reason it doesn't is because the satellite has to be moving at such a great speed, something like 8 kilometers per second, so that the Earth falls out from underneath it as it starts to fall. Okay? The curvature of the Earth makes it so that as this satellite begins to fall, in the time it would normally take an object to fall, the satellite's already moved so fast that it begins to fall off the edge of the Earth, like this. Okay? So because it's falling off of the Earth, and the Earth's curving away from it, it just falls in the direction of its orbit. Okay? When it gets to this point over here, it's the same thing here. We would normally expect gravity to pull it downward, but because it's traveling so fast, by the time it would normally fall down, it's already falling this direction. Okay? So the Earth is always dropping off beneath the satellite, so it's always falling into empty space. Thus, we get the circular orbit. Okay, hope that made sense. I feel like that was a little bit better than I had the chance to explain in class. Cool. What did we talk about next? We talked about fluids and pressure. Okay, let's go there. So with fluids and pressure, oops, wrong window. Fluids and pressure. You might be asking yourself, why are we talking about fluids when this is a unit on forces? Well, we're going to talk about how fluids exert forces on objects. Okay, so a fluid is basically any substance that takes the shape of its container and flows easily in its particles. So even though we commonly associate fluids with liquids, fluids can be gases because they take the shape of their container and the particles flow very easily. Okay, so the reason we talk about this, whenever we have any container, or the Earth, for example. So here's a container, here's the Earth. Let's say I have a fluid in here with all these particles that take the shape of the container. As these particles take the shape of the container, they're pressing on the container. Okay, remember that any push or pull is a force. So particles in a fluid have a force that is being exerted on the container. Now, we call that force pressure. Pressure is basically the force of an object over a given area. Okay. Now, on the Earth, because we classified gas as fluids, you see particles of gas around the Earth. Okay. Now, gravity is pulling these particles towards the center of the Earth. Okay. So, because of this pull, we start to see more dense particles towards the Earth's surface, and more spread apart particles farther away from the Earth. Okay? So very near the surface of the Earth, the air pressure is greater because there's a lot more particles pressing on us, pressing on the surface of the Earth. As we get farther away from the Earth, the air pressure decreases. Now, in our wind chapter, we already talked about what generates wind. Basically, particles flowing from high pressure areas to low pressure areas. So we won't discuss that right now. But what we will discuss is water pressure. Okay, so imagine here I have the ocean, and there's air particles above the ocean. They are pressing down on the surface of the water because of gravity, and we also see the same kind of effect in the water. Our particles in the water get very dense the closer you get to Earth's surface because gravity's pulling on them. Okay, so we see kind of this downward pressure or force in both air and water. So any object down at the bottom of the ocean, like let's say an aluminum can, is going to be experiencing air pressure pressing down on the water, which presses down on the can. So this explains why, water pressure is very dangerous for submarines if they're not built correctly, because that's a lot of water and air that's pressing down on an object down there. Let's see, what else? We talked about the classic example of a straw that demonstrates how pressure and fluids are impacted. If you've got a straw and there's particles in the liquid, there's particles in the air. We already said that air pressure can be exerted on a fluid. Now, as you suck through a straw, you're basically removing particles from the straw itself, which basically causes an unbalanced force between the pressure inside the straw and the pressure on the liquid. So as you eliminate particles, so I'm going to call this a vacuum because you've just sucked out particles or removed them, the pressure on the water outside the straw is going to be such that it will push the water up the straw and into your mouth. Okay? And it's all because we get particles moving from high pressure areas into low pressure areas in the straw. Okay, giving some pretty good examples of pressure. Let's see here. I gave you an equation. Sweet. I think we might be done. Oh, no, we're not. Got one thing. In fluids, we have what's called a buoyant force. Okay? So you'll notice, since water is a fluid, excuse me. Excuse me again. Since water is a fluid, we see objects that sometimes float on water. So here's my little sailboat. So if objects can float on water, even though gravity is being pulled on them, there must be some force that's pushing an object to make it stay on top of water. Okay? Now with a table, we call this the normal force. On a fluid, we'll call it a buoyant force. So basically, the force that a fluid pushes upwards on an object. Okay. Now, objects will sink or float primarily due to their density. Okay. So density, if, let's say, our boat, we'll say density of our boat, if that's less than the density of water, then the boat will float. Okay, because heavier objects, or more dense, I should say, more dense objects tend to sink. Okay, if the density of our boat is equal to the density of water, the boat neither sinks nor floats. And it doesn't float, but it doesn't sink. Okay, so submarines can achieve a density that's equal to water, so they can stay where they are. And if the density of the boat is greater than the density of water, the boat sinks, of course. Okay, that's pretty common knowledge, but hopefully that makes sense. If not, turn to your book and review it. And the last thing we're going to talk about today is called Archimedes' principle. Archimedes was a Greek mathematician who understood the buoyant force and tried to quantify it with an experiment. Okay, so according to Archimedes' principle, the buoyant force on an object by a fluid equals the weight of fluid displaced by the object. Okay, so in our lab and the other day in class, we filled a cup to the brim with water. We stuck an object, let's say we stuck like a little dice in the water. Here's my little dice. As we stick that in the water, we're going to have some water overflowing over the sides. If we were to catch that water that's spilling over and weigh it, we would be able to quantify the buoyant force. Okay? So, yeah. If you can remember the experiment we did in class, you're going to be fine. But just know that the weight of water displaced by an object is equal to the buoyant force of the fluid on the object. Cool. Alright. Wow, we covered a lot in this little review. So, I hope that helps you get ready for your test tomorrow. If you have any questions, bring them to me tomorrow, hopefully before class, so we can answer them before you take your test. Until then, thanks for watching, and good luck studying.